This is the second in the series of topic videos for ERTH 425-625 week 1. In this shorter video, we're going to talk about elemental cycles, things like, for instance, the carbon cycle, and how we use the concepts of cycles, reservoirs, and fluxes to look at individual chemicals as they move between the various spheres of the Earth. So when we can think about cycles, we can, for elements, we can do them on a global or a local basis, or something in between, regional for instance. These can be constructed in a variety of ways, using different specific reservoirs as needed for the particular application that we're working on. And these general examples, I'm going to focus on global cycles, just to kind of get you thinking about them. But we're going to use cycle thinking throughout the semester, so this concept will come up over and over again. As I mentioned previously, cycles should be closed, meaning that we can account for all the material. Sometimes this is easier said than done when we have to actually go out and make measurements of the amount of, for instance, carbon that goes between the atmosphere and the biosphere every day, or every year, or whatever time frame we're looking at. So sometimes there are some assumptions that are made which make the cycles less good than a perfect cycle, but better than not having a closed cycle at all. We'll look at a few examples of some particularly important elemental cycles that are involved with life, so biogeochemical cycles. And it's important to recognize that when we look at a cycle diagram for a particular chemical in a particular application, we won't necessarily find all the spheres, the geosphere, hydrosphere, atmosphere, biosphere, anthrosphere, etc. And sometimes we'll see some of those traditional spheres divided up into subspheres. For instance, the oceans may be separated from fresh water. It all, again, depends on the application that we're talking about. So this is a pretty common example of something that you probably recognize as the carbon cycle. It tracks carbon in various forms, going from the atmosphere into growing plant material on the land surface and respiring organisms such as that cow shown there on the land surface. There is carbon bound up in the soil in organic matter and inorganic matter. There's dissolution into the oceans. There's some form of industrial process producing a plume that's sending carbon back up from the atmosphere. There's burial of carbon into fossils and fossil fuels. This isn't a complete iteration of the carbon cycle. There are also inorganic forms of carbon, such as calcium carbonate, that can be found in soils and in rocky substrates that is not shown here, for example. But this is a depiction of the kinds of processes that help to move carbon about from an inorganic form in the atmosphere as carbon dioxide to organic forms found at the surface of the Earth. Now, this is a slightly drier but perhaps more informative way of looking at the carbon cycle. In this case, we're looking at the types of carbon from a very chemical perspective. And you don't see any reservoir names on here in most cases. I've highlighted some. You can see at the top carbon dioxide in the atmosphere. That's obviously the atmosphere. But pretty much all of the other boxes, and there are processes on there. You can see photosynthesis, which was depicted by trees on the last diagram. And you can see biodegradation, which is the breakdown process. For remineralization, we call it, of organic matter. But you'll see that the other reservoirs here are not specifically identified. So the boxes include something called fixed organic carbon. Carbohydrate in brackets there represents, for instance, sugars and glucose like compounds, as well as polysaccharides, things that make up cellulose fiber, for instance. And we'll talk about more that later in the semester, what we define by that. There's a whole host of chemicals there. That is thought of as carbon in both living tissue as well as dead tissue. So some of that might be in the biosphere, some of that might be in the geosphere. We also have soluble inorganic carbon, predominantly as bicarbonate anion. That's in the center part of the diagram. That's obviously carbon dissolved in water. And then we see two boxes highlighted in brown. One says fixed organic hydrocarbon and kerogen. This is, for instance, petroleum and the like. And insoluble inorganic carbon, predominantly calcium carbonate and calcium magnesium carbonate. So those are both in the geosphere. And you'll see a bunch of processes written there in italics, which represent the things that cause fluxes from one form to another. Now, neither of these diagrams, this one or the one on the prior slide, actually has any quantities on it, but they're giving you an idea of, in concept or a conceptual reconstruction of how carbon moves about on the surface of the planet. Now, this is a rendition of the nitrogen cycle, very similar to that first carbon cycle picture I showed you, with various arrows showing you how nitrogen moves between the atmosphere, dissolved in water, nitrogen in soils, and nitrogen in the biosphere, as well as anthropogenic impacts on emissions. And you'll also see across the bottom that there are 3 different chemical forms of nitrogen that can be found in both soils, the kind of brown area on the diagram, and water, the blue part of the diagram, nitrate, nitrite, and ammonium. Each one of them is formed by and consumed in very different processes, and so it's oftentimes useful to look at them separately instead of nitrogen all together. Now, this is the equivalent diagram from the textbook, showing you in a somewhat condensed version the various forms of nitrogen that we find in the atmosphere, the various forms impacted by human activities in the atmosphere, the kinds of nitrogen that we find in the biosphere, and the kinds of nitrogen that we find in both the hydrosphere and geosphere, which are pooled together, as well as fluxes between them and different kinds of processes involved in those exchanges. I encourage you to pause the video and read the text on those various fluxes to make sure you understand the kinds of things that are happening for each one of them. Now, this is a depiction of the phosphorus cycle. Again, it's rather complicated. It has various forms of phosphorus, and again, just like for nitrogen, we can separate out inorganic phosphorus, such as phosphate, various forms of HPO4. It can be HPO4 in various anion forms or as phosphoric acid H3PO4. These are all conjugate bases of each other. We can also have organic forms, what we call organophosphorus compounds. And in that red box where we see the atmosphere, we see 2 kinds of phosphorus. Phosphorus that comes from our introduction of inorganic phosphorus into the environment, such as through soaps and detergents. This is primarily the phosphate form, as well as xenobiotic phosphates, which are primarily organic. Now, xenobiotic, as you can imagine from the term xeno, which often means foreign or not normally part of that system. Think about a xenophobe, or if you're familiar with the geologic term xenolith, foreign rock in an environment. A xenobiotic compound is one that's not formed by organisms, and many forms of phosphorus that are used by humans, especially things like pesticides, various other phosphorus-bearing compounds that are used in the formation of microchips, for instance, are released into the environment and they become xenobiotic. They behave differently than the inorganic phosphorus, so they're shown in a different box in the center of the diagram. You'll also see phosphorus bound up in various biomolecules, phosphorus found in rocks, and in various forms shown in different colors there, and a depiction of what reservoir we might consider them to be a part of. Finally, this is a rendition of the sulfur cycle. We'll talk a lot about each one of these cycles, the nitrogen, the phosphorus, and the sulfur. The sulfur cycle is really interesting because humans have, primarily through fossil fuel burning, but also through our extraction of mineral ores from the planet, dramatically changed the sulfur-bearing content of the atmosphere. And sulfur, in all of its forms, is acidic. So this is one of the main contributors to acid rain. And you can see here that sulfur is found, just like nitrogen, in a variety of oxidation states in the atmosphere. It can be also found in various forms in the biosphere. It can be found bound up in rocks in both organic material and inorganic material in the geosphere. It can be found in xenobiotic compounds. And there are, as in the other diagrams, various ways for these chemical forms to be transformed between the reservoirs by different sorts of processes.